In this video, we're going to continue using Clifford algebras to generalize the complex numbers and quaternions to spin groups, which help us do rotations in any dimension. The unit length complex numbers are actually the group spin 2, because they give us rotations in 2D space. The unit length quaternions are actually the group spin 3, because they give us rotations in 3D space. The spin n group is the generalization of these that gives us rotations in n-dimensional space. We'll define spin groups using Clifford algebras, which are algebras where the basis vectors square to +1 or -1, and where orthogonal vectors anti-commute with each other. It turns out that it's better to view the complex I as the Clifford bivector sigma x sigma y, which represents a rotation in the xy plane. The unit quaternions are also better represented as bivectors. Instead of rotating around axis I, we should think of rotating in the yz plane. And instead of axis j, we think of the zx plane. And instead of axis k, we think of the xy plane. The bivectors also multiply together to give us the standard quaternion multiplication rules, because of the anti-commutative property. Since bivectors in Clifford algebras always give us rotations, we can extend this pattern to work in any dimension n, where the bivector sigma a sigma b gives us a rotation in the AB plane. This is how we define the spin n group. We can also generalize this to spacetime. The group spin 1, 3 gives us both rotations and Lorentz boosts in 1 time dimension and 3 space dimensions. Its generalization is spin pq for rotations and boosts in p time dimensions and q space dimensions. In this video, I'm going to show how Clifford algebras can be used to do reflections and rotations on vectors in any dimension. This explains why Clifford algebras are also called geometric algebras, because they allow us to easily perform geometric operations on vectors. Some of this video's content was already covered in video number 6, when I introduced the Pauli matrices and Pauli vectors. But that video relied on matrices to do rotations. This video will involve no matrices and only use abstract symbols from the Clifford algebras to do geometric operations. Before we start, I'd like to go over some names we give to various members of Clifford algebras, just so we're on the same page when I use them later. The standard building block in Clifford algebras is the vector, which belongs to some vector space V. Vectors combined together with the wedge product give us bivectors, trivectors, or general k-vectors, also called k-blades. The grade of a k-vector refers to how many vectors appear in the wedge product. An arbitrary sum of k-vectors is called a multivector. When we have a Clifford product of vectors, we call this a versor. Note that the Clifford product of two vectors is not the same thing as a bivector, since the Clifford product gives us the sum of a scalar and a bivector. The Clifford product and wedge product are only the same if the two vectors are orthogonal, and the dot product part goes to 0. With this out of the way, let's get started with learning about rotations and reflections in Clifford algebras. To start, let's look at CL30, the Clifford algebra in 3D space, with 3 orthonormal basis vectors that square to +1, which are sigma x, sigma y, and sigma z. And when we multiply 2 different orthogonal basis vectors together, we can switch their order if we include a negative sign, since multiplication of orthogonal vectors is anti-commutative. Let's start with performing vector reflections. We reflect vectors by performing negative conjugation on them using the vector we want to reflect along. Let's see how this works. If we want to reflect a vector along the z-axis, this means we leave the x and y components the same, but change the sign of the z component. So this is like if the plane perpendicular to z, the xy plane, is a mirror that we're reflecting in. reflection of a vector v along the z direction is done using negative conjugation by z, which means we multiply by sigma z on the left and sigma z inverse on the right, and include a negative sign in front. For example, reflecting sigma x along sigma z looks like this. The colors don't mean anything here, they're just to make the formula more readable. Since sigma z multiplied by itself gives +1, this means sigma z is its own inverse, so we can just drop the inverse operation. After swapping, we get an additional negative sign in front, which cancels with the first negative sign. Also, sigma z squared gives us +1, so we get sigma x as a result. It makes sense that sigma x is unchanged when we reflect it in this mirror associated with sigma z. The same is true for reflecting sigma y along the z-axis. But if we want to reflect sigma z along the z-axis, sigma z immediately cancels with sigma z inverse, and so we get negative sigma z. So the sigma z basis vector has been reflected as expected. If we take a general vector v, which is a linear combination of sigma x, sigma y, and sigma z, and reflect it along z with a negative conjugation, the x and y parts are left unchanged, but the z part is reflected and gets a negative sign, as expected. Now, when we're doing reflection along a unit vector that squares to 1, such as sigma z, its inverse is not required in the conjugation formula. However, if we reflect along a vector u, which doesn't have unit length, we need to properly calculate the inverse. We know u times u equals the squared length of u. We can multiply on both sides by u inverse, cancel u and u inverse, and then divide by the squared length. So u inverse equals u divided by the squared length of u. For example, if we reflect along 5 sigma z, its squared length is 5 squared, so the inverse is 5 sigma z over 5 squared. In the negative conjugation, each factor of 1 over 5 serves to normalize the vectors in the reflection formula if they are not already normalized. So we get the same reflection formula as if we had just reflected along a unit length sigma z vector. We can prove this reflection formula works for any invertible vector u. We break v into portions parallel to u and perpendicular to u, then distribute. The parallel portion of v can be written as a scaled version of u using a scale factor k, and the perpendicular part of v will anti-commute with u, so we can swap their order and change the sign. U and u inverse combine to 1 here and here, and we can rewrite k times u as the parallel portion of v. The result is v, where the portion parallel to u is reflected with a minus sign, and the perpendicular part is unchanged, as expected. So this negative conjugation formula breaks a vector v up into parts parallel to u and perpendicular to u, and it only reflects the part parallel to u. We can also confirm that this reflection formula keeps the length of v unchanged. If we take v times v and then reflect both v's, the negative signs cancel, and the inner u inverse cancel. V times v gives the squared length of v, which is a scalar that can be moved here, so that u and u inverse cancel. So the squared length of v is unchanged by reflection. Now let's look at spacetime, which has the Clifford algebra CL13. This has 1 dimension of time and 3 dimensions of space, given by the orthonormal basis vectors gamma t, gamma x, gamma y, and gamma z. According to the plus minus 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 metric, the time basis vector squares to +1, and each of the space basis vectors square to -1, and the basis vectors anti-commute with each other. We could also choose to work in CL31 if we wanted, which uses the mostly plus metric convention. But for this video, I'm going to work in CL13, which has the mostly minus convention. Let's review some of the basics of special relativity. The lengths of spacetime vectors are measured using the spacetime interval formula, given here. As an exercise, you can check that we get this formula when we square a spacetime vector, and that the Clifford algebra symbols give us all the correct signs. Looking at a spacetime diagram, the time-like vectors that point to the future or the past have positive squared lengths. Space-like vectors that point in spatial directions have negative squared lengths. And light-like vectors that point along light beams have 0 squared lengths. It's very important to remember what orthogonality looks like in space-time. In ordinary space, two vectors are orthogonal if they meet at right angles. In space-time, a time-like vector and a space-like vector are orthogonal if they make equal angles with a beam of light. This affects how reflections work in space-time. In ordinary space, a reflection vector defines a mirror that is orthogonal to it. When we reflect a vector in the mirror, the initial and reflected vectors form equal circular angles with the mirror. In space-time, a reflection vector also defines a mirror that is orthogonal to it. But recall, orthogonality means forming equal angles with a light beam. So the mirror looks like this. When we reflect a vector in the mirror, the initial and final vectors form equal hyperbolic angles with the mirror. So this is a little more complicated than physical space, but the basic idea is the same. The reflections in space-time are done exactly as before with negative conjugation. However, note that the inverse operation on the right is always required. If we reflect with a space-like vector, its squared length is negative, and this negative sign is important to keep track of in the reflection formula. Gamma x, for example, is a space-like vector. This means that the inverse of gamma x is actually negative gamma x, since gamma x squares to -1. This extra minus sign in the inverse is important to keep track of. If we try to do a reflection, this extra minus sign will cancel out with the minus sign we get from squaring gamma x, ensuring that our result has the correct sign. Also, some vectors in space-time, such as gamma t plus gamma z, square to 0. These are the light-like vectors which point along the paths of light beams in space-time. Because their squared length is 0, light-like vectors have no inverse, and so we cannot use them to reflect along for reflections. You can think of a light-like vector as existing at an infinite hyperbolic angle. So we can't use it to measure hyperbolic reflection angles with our initial and final vectors. So reflections of vectors in physical space and space-time both use the same negative conjugation formula. This negative conjugation works in all Clifford algebras of any dimension as well, not just 3D space or 4D space-time. Now let's look into doing rotations in physical space with CL30. A rotation can be thought of as a pair of reflections. For example, if we take this flag and reflect it in this mirror, then take the result and reflect it in this mirror, we end up with a rotation of the original flag. So if we want to rotate something, all we need to do is do a pair of reflections. Also notice that the angle of the flag's rotation is twice the angle between the two mirrors that we used. So if we want to do a rotation by some angle theta, all we need to do is pick two reflection vectors that are at an angle of theta over 2 apart. Let's say we want to do a rotation by angle theta in the xy plane. First we reflect along the x-axis with sigma x. Then we reflect along a unit vector tau, which forms an angle of theta over 2 with sigma x. In other words, tau equals cosine theta over 2 sigma x plus sine theta over 2 sigma y. So let's see what our rotation formula looks like on a vector v. First we reflect along sigma x, then we reflect along tau. The two negative signs in the double reflection cancel out. Also, it's a rule in algebra that the inverse of a product is the product of the inverses written in the opposite order. This causes the terms in their inverses to cancel out one by one. So we can rewrite sigma x inverse times tau inverse as the inverse of tau times sigma x. Note that our rotation formula is also a conjugation formula, with a product of vectors on the left and the inverse of that product of vectors on the right. We'll call this product of vectors a versor, which is a word we'll talk more about later. The angle between the two vectors in the versor is half of the rotation angle. So it's as if each versor does a rotation of theta over 2, and they combine to do a rotation of theta. Now let's plug in our definition of tau into the rotation formula. We can distribute the sigma x. Recall that sigma x squared equals plus 1, so we get this. As a final step, I'm going to reverse the order of the sigmas and introduce a negative sign, so that it reads negative sigma x times sigma y. This reminds us that the rotation is in the orientation that brings the positive x-axis towards the positive y-axis. Now, let's look at what we have so far. We know rotations are done using conjugation with a product of a pair of vectors. And this pair of vectors is sometimes called a versor. The versor can be written using a pair of vectors like this, or in expanded form using cosines and sines. Note that this versor is not a bivector in general. A bivector is given by the wedge product of two vectors. But the versor is given by the Clifford product of two vectors, which has a dot product part that results in a scalar, and a wedge product part which results in a bivector. Now, what is the inverse of this versor? Recall that we can write the inverse of a product as the product of inverses in the opposite order. Recall, sigma x and tau are not always orthogonal, so we cannot swap them in exchange for a negative sign. However, since sigma x and tau are both unit vectors that square to plus 1, they are their own inverses. So in this special case of unit vectors, the inverse of the versor involves just swapping the order of the vectors. We can also apply this logic to our formula with sines and cosines. We get the inverse just by swapping the order of the sigmas. Since sigma x and sigma y are orthogonal, we can swap them in exchange for a negative sign if we want. Sigma x times sigma y also squares to negative 1. So it's similar to the complex I, and the reversal operation is a bit like taking the complex conjugate. In the special case where the versor is made up of unit vectors, we can replace the inverse operation with a reversal operation, which is often written as a tilde or a dagger, the dagger taking inspiration from the Hermitian conjugate, which is known to reverse the order of Pauli matrices. However, what if we used a versor that is not made of unit vectors, such as 5 sigma x times tau? The inverse in this case is not just the reverse. We need to include additional numerical factors, because the vectors don't have length 1. The inverse ends up being the reverse, tau times 5 sigma x, all over 5 squared, which is the squared magnitude of 5 sigma x. Just like we saw with reflections, each factor of 1 over 5 will normalize the vectors on either side, making the formula the same as if we rotated using a versor made up of only unit vectors. Now let's explicitly check that this formula actually works. We can distribute v over the left brackets. Since cosine is just a scalar, we can bring v to the other side for free. For the sine term, things are more complicated, depending on whether or not v is in the plane of rotation. If v is not in the plane of rotation, for example, v equals sigma z, then we do 2 flips here, picking up 2 negative signs that cancel out, and the result is unchanged. In other words, if v is not in the plane of rotation, we can move v to the other side of this expression without any changes. These two expressions are inverses of each other, and so they cancel out, leaving v unchanged. So if the vector v is outside the plane of rotation, This rotation formula does not affect it. However, if v is in the plane of rotation, for example sigma x, then we only pick up one negative sign while doing the swapping, since swapping a basis vector with itself does nothing. In this case, we do end up with a sign change. We can factor sigma x out in front, and as we showed before, taking the inverse of this expression is the same thing as changing the sign in front of the sigmas. So now, instead of the vector being unchanged, we have the vector times this product. Distributing, we get cosine squared plus 2 cosine sine times the xy bivector plus sine squared with the xy bivector squared. As discussed before, the xy bivector squares to -1, leaving us with negative sine squared. The result involves the double angle formula for cosine and the double angle formula for sine. So the angles of theta over 2 get doubled to theta. After we distribute the sigma x, the cosine term gets sigma x, and the sine term gets sigma x squared, which goes to 1, leaving it with only sigma y. This results in the original vector rotated by an angle theta, as expected. If a vector has parts both inside and outside the plane of rotation, only the part inside the plane of rotation will be affected by this formula. So, in conclusion, this double-sided operation will rotate vectors within the plane of rotation and ignore vectors outside the plane of rotation, as expected. We can get similar formulas for the YZ and ZX planes. But remember, you can always rotate in any arbitrary plane of your choice. Just pick two vectors in that plane, A and B, and ensure they are separated by an angle of theta over 2. You can then double reflect along each of these vectors, and this is equivalent to doing a rotation by an angle theta in the AB plane. Now, let's look back at our formula for rotating in the XY plane. This expression here has a lot in common with Euler's formula, which says that e to the I times an angle equals cosine plus I times sine. The reason that this is true is due to the fact that I squares to -1. It turns out that sigma x times sigma y also squares to -1. So these formulas are very similar, and it turns out that we can write this expression as e to the sigma x sigma y theta over 2. Let's recall the Taylor series of e to the x. We get an infinite polynomial in x with factorials in the denominator. If we do e to the I theta, then the first term with the 0 power goes to 1. The first power gets an I out in front. The second power gives us I squared, which is -1. The third power gives us I cubed, which is I squared times I, which is just -I. And the fourth power gives us I squared twice, which is -1 times -1 equals +1. This pattern of 1, I, -1, -I repeats forever. If we separate the terms without I from the terms with I, the series without I is the Taylor series for cosine, and the series with I is the Taylor series for sine. This is the proof of Euler's formula. If we do this exercise again, but with replacing I with sigma x times sigma y, it works out the exact same way, since the bivector sigma x sigma y also squares to -1. So Euler's formula doesn't just work for I, it works for any symbol that squares to -1. Also note that if we use a negative angle in this formula, the cosine term is unchanged since cosine is symmetric. The cosine of an angle and its negative give the same result. The sine term, however, can have the negative sign moved out in front, since sine is an antisymmetric function. So we can replace these formulas with a negative exponential and a positive exponential involving the bivector sigma x sigma y. This exponential version of the formula works for rotating in any plane given by two sigmas. More generally, the rotation formula can be performed with any general unit bivector b that squares to -1. Recall, a bivector represents an oriented plane, given by the wedge product of two vectors. The bivector's orientation in space gives the plane and direction of rotation. The theta over 2 scales the size of the bivector to the size required for rotating by an angle theta. One way to get the required bivector in 3D is to write out a unit vector for the axis of rotation, and then replace the basis vectors with the corresponding orthogonal bivector planes. After being exponentiated, the bivector becomes a versor, and this is what performs the rotation. Now, you might be confused about this double-sided transformation. If we want to rotate a complex number, a plus ib, we just do a single-sided multiplication by e to the I theta. Since complex numbers commute, we can also write this as a double-sided transformation with e to the positive I theta over 2 on both sides. So why do the signs look different in Clifford algebras? The key is to realize that in the xy plane, the complex I is just the bivector sigma x times sigma y in disguise. In the complex number approach, both the rotator and the object being rotated are a scalar plus a bivector. In Clifford algebras, the object being rotated is a vector instead. We can make the two equivalent if we pre-multiply this vector by sigma x. This explains where the sign change comes from. Swapping order with a sigma x introduces an extra minus sign. Now let's look at the rotations in four-dimensional spacetime with CL13. In spacetime, we should be able to do 3 rotations, as well as 3 Lorentz boosts. The rotations here work the same way as in 3D space. If we want to rotate in the xy plane, we just use the cosine and sine formulas using the bivector gamma x gamma y, which squares to -1. Since this bivector squares to -1, we can also use the exponential formulas that we discussed previously. But what if we use a bivector that involves the time basis vector gamma t? What happens if we try to do a rotation where the bivector involves the time basis vector and one of the space basis vectors? If you guessed Lorentz boosts, you are correct. These 3 bivectors involving the time basis vector give us Lorentz boosts in the 3 orthogonal directions. But let's look at this exponential formula more closely. Gamma t times gamma x actually squares to +1, not -1. Flipping the inner terms gives us a negative sign, but this cancels with the negative sign we get when gamma x squares to -1. And since gamma t squares to +1, the answer is +1. So what happens when we take the exponential of a symbol that squares to +1? We can check this using the split complex number j from the last video, where j squares to +1. When we write out the infinite Taylor series of e to the j phi, the 0th power goes to 1. The first power gets j in front. The second power gets j squared, which is +1. The third power gets j cubed, which is just +1 times j. And the fourth power gets j squared twice, which is just +1. This pattern of 1j, 1j continues forever. Notice that all the signs are positive this time. If we separate the terms without j's from the terms with j's, the terms without j's give us the Taylor series for hyperbolic cosine, and the terms with j's give us the Taylor series for hyperbolic sine. As discussed in video 9, Lorentz boosts are just another word for hyperbolic rotations. So this result is indeed a Lorentz boost. If we replace the symbol j with the bivector gamma t times gamma z, which also squares to +1, we get a similar formula involving hyperbolic trig functions, which represents a Lorentz boost in the z direction. We can get similar formulas for boosting in the x and y directions. It also turns out that putting a negative sign in the hyperbolic angle gives us the same formula, but with a negative sign in front of the sine h term. So we can also rewrite the Lorentz boost formula using exponentials. A boost in the I direction is given by exponentiating a bivector formed with gamma t and gamma I. More generally, a boost is performed by exponentiating a unit bivector that squares to plus 1. To get this unit bivector, one axis must be time-like and the other must be space-like, and the boost is done in the spatial direction contained in the bivector. The angle phi over 2 scales the size of the bivector that's required for doing a boost by a hyperbolic angle of phi. Now, bivectors can be used for both boosts and rotations. So how can we tell which bivectors do what? If a bivector squares to a positive number, it performs a boost, since the exponential gives us a hyperbolic rotation similar to the split complex number j. If a bivector squares to a negative number, its exponential performs a circular rotation, similar to the complex number I. Before moving on, I'd like to say a few things about how boosts are visualized as a pair of reflections. You might think that a boost in the x direction is given by reflection along x, and then a reflection along t. But this changes a future pointing vector into a past pointing vector, which doesn't make sense for a boost. It's actually impossible to end up with such a transformation using our boost formula, because hyperbolic cosine never gives 0. If we rearrange this formula, we see that a boost is given by two reflections with two time-like vectors. Since hyperbolic cosine is always larger in size than hyperbolic sine, we know for sure this vector I'm labeling as delta is a time-like vector. So a boost is given by two time-like reflections. One reflects us into the past light cone, and another reflects us back into the future light cone, with the boost's hyperbolic angle being twice the angle between the two time-like vectors. As a very quick aside, when we have a symbol epsilon that squares to 0, we get the dual numbers. And these can be used to do Galilean boosts from Galilean relativity. You can pause if you want to look at the details, but the matrix representation of epsilon helps us build a Galilean matrix that changes coordinate frames according to Galilean relativity. We can do double-sided transformations that perform Galilean boosts, which can also be written with exponentials. So, using Clifford algebras, we've discovered how to do rotations in 3D space, and also how to do rotations and boosts in 4-dimensional space-time. And it's not difficult to see how we can generalize these formulas to any arbitrary dimension. In any dimension, if we want to rotate in a plane, we just take a bivector of size 1 in that plane and exponentiate it, and apply this double-sided transformation with half angles. The members of Clifford algebras that do these rotations using double-sided transformations are part of that Clifford algebra's spin group. For example, the exponentials that do rotations in CL30 are part of the group spin30, and the exponentials that do rotations and boosts in CL13 are part of the group spin13. Generally speaking, the members that do double-sided rotations in CLPQ are part of the group spinPQ. But what is the formal definition of these spin groups? We'll start by defining the spin n group, which lives inside the Clifford algebra CLN, which has n basis vectors that square to +1 and anti-commute with each other. We already know the formula for reflecting a vector v in the Clifford algebra CLN. We just negative conjugate it with a reflection vector u. If u happens to be a unit vector that squares to +1, then u is its own inverse, and we can forget about the inverse operation. However, if u is not unit length, then it squares to its squared length, and so u inverse equals u over its squared length. This forces both copies of u to be normalized by its length, giving a formula that does involve unit vectors. In this scenario, we call U a versor of length 1. Next, we learned that a rotation is just a pair of reflections. So we can rotate by doing two reflections with U2 and U1. The negative signs cancel, and we know the product of inverses is just the inverse of the product in the reverse order. Here I'll call U1, U2 a versor of length 2. If U1 and U2 are unit vectors that square 2 plus 1, then they each equal their own inverses. So the inverse of U1, U2 is just the reverse, U2, U1. This is sometimes denoted with a tilde or a dagger. So we can write the rotation formula like this. However, if U1 and U2 are not unit length, then multiplying by the reverse doesn't give 1. Instead, it gives the product of the squared lengths of the vectors. The inverse is then the reverse divided by the squared lengths. As before, these squared lengths normalize the vectors so that they have length 1. If we do 3 reflections with U3, U2, U1, this equals a rotation plus a reflection. Only 2 of the negative signs cancel, and so we end up with a negative out in front. Here we have a versor of length 3. Again, if all of these are unit vectors, we can write the inverse as just the reverse. But for non-unit vectors, the inverse requires division by the squared magnitudes, so that the vectors become normalized. If we do 4 reflections, this equals a pair of rotations, which combine together to just give another rotation. We get no negative sign in front and a versor of length 4. The rules for inverse are the same as before. And we can keep going with larger and larger versors. So the rule is, if we have a versor with an odd length, then we get a reflected rotation, and our formula requires a minus sign in front. If we have a versor with an even length, we get a pure rotation, and our formula has no minus sign. One issue with these formulas is that there's an infinite number of versors that do the same transformation. For example, reflecting along U, 2U, 5U, and 100U all do the same thing. We can reduce this infinite number of choices if we force the vector U to have unit length. In this case, there are only 2 vectors that can do the same reflection, plus U and minus U. Since the transformation is double-sided, the 2 minus signs in minus U will cancel out, so it gives the same transformation as plus U. The same is true for rotations. If we force the versor U1, U2 to be made up of unit vectors, then there are only 2 choices of versor that perform a given rotation, the plus and minus versions of U1, U2. This extends for versors of any length. If the versor is built using only unit vectors, there are only 2 versors that will do the same geometric transformation, the plus and minus signs of the same versor. Also, to get the inverse of versors made up of only unit length vectors, we just take the reverse. We say that the set of versors of even length that are made up of unit vectors is called the spin group. This contains all possible rotations that can be done in n-dimensional space. Spin n is the double cover of the rotation matrix group SON, which is the special orthogonal n by n matrices. We say spin n is the double cover because there are 2 members of spin n that perform the same rotation as a given SON matrix. Because positive and negative versions of a versor do the same rotation, they are both associated with a single rotation matrix. If we expand the set to include all versors of both even and odd lengths, made up of unit vectors, we call this the pin n group. This contains all possible rotations and reflected rotations that can be done in n-dimensional space. Pin n is the double cover of the orthogonal group ON, which includes rotations and reflected rotations. Again, it's the double cover because there are two versors in the pin n group for every ON matrix that performs the same geometric operation. The plus and minus versions of the same versor perform the same geometric operation. The reason we call it the pin n group is a bit silly. The SON group does pure rotations. To include reflected rotations, we just cross off the S to get ON. Similarly, the spin n group does pure rotations. To include reflected rotations, we just cross off the S to get the pin n group. One thing that's a bit awkward is that we have two different formulas for reflected rotations and pure rotations. One has a negative sign and the other doesn't. We can merge the two formulas into a single formula if we introduce a new operation called grade involution for Clifford algebras, which is usually denoted by alpha or a hat symbol. The grade involution just takes a vector and gives it a negative sign. If you apply it to a product of vectors, then they each get the negative sign. If you apply it to a product of two vectors, then they each get a negative sign, which cancel with each other, so there is no overall sign change. In the case of three vectors, two of them cancel and there is an overall sign change. With four vectors, all the minus signs cancel and there is no sign change. The grade involution formula basically swaps the signs of odd grade members and leaves the sign unchanged for even grade members. So by applying grade involution to the first versor in a conjugation, we automatically get the correct sign depending on if U is even grade or odd grade. So this conjugation with a grade involution allows us to perform both reflected rotations and pure rotations in a Clifford algebra of any dimension. A conjugation that includes this grade involution is sometimes called a twisted conjugation. Now, we just need to put in a little more work to generalize this to spacetime in a Clifford algebra CLPQ, with p time dimensions and q space dimensions. As discussed previously, the reflection and rotation formulas work the exact same as in physical space. Negative conjugation with a vector for a reflection, and positive conjugation with a grade 2 versor for a rotation. We can define the spin PQ group almost exactly as before, even grade versors made of unit vectors. However, unit vectors include both time-like unit vectors that square to +1 and space-like unit vectors that square to -1. This means that for members of the spin PQ group, an element multiplied by its reverse won't always give +1. It will sometimes give -1. For example, if the transformation contains a boost. Sometimes we define the spin plus PQ group to only include members who multiply with their reverse to give +1, and the -1 case is excluded. The pin PQ group is simply defined as all versors of any length made of unit vectors. As expected, spin PQ is the double cover of SO plus PQ, where the plus indicates that time reflections are excluded, and pin PQ is the double cover of OPQ, which includes both space and time reflections. It's important to keep in mind that for spacetime, if a vector is space-like and squares to a negative number, then its inverse will have an extra negative sign. So we always require these inverse operations to get the signs right in our equations. Taking the inverse of a space-like vector requires dividing by the squared length of the vector, and this will give us the extra required negative sign. So we've learned that we can transform a vector v using twisted conjugation with a versor r. It turns out that we can also transform any general multivector m using a similar transformation. Let's start by assuming the versor r has an even length, and so the grade inversion doesn't change the sign. If M is made up of vectors v, w, x, y, we can transform each individual vector using conjugation. The inner conjugation terms of R inverse and R cancel with each other, and we're left with only the outer R's. So conjugating each individual vector in M is the same thing as conjugating M itself. This allows us to transform bivector planes, trivector cubes, and so on, with the same conjugation formula. The quaternions I, j, k can be written in terms of bivectors and rotated with the standard conjugation formula just like a vector. But now, what if the versor R has any length, so its grade inversion can lead to a plus sign or a minus sign, depending on its length? If we take the individual vectors that make up M and twisted conjugate each one, we get a bunch of R's with grade involution acting on them. One way to write grade involution is to take R times -1 to the power of the length of R. This way, even length R's get a plus sign and odd length R's get a minus sign. If we have 4 grade involutions multiplied together, we get the same result, just taken to the 4th power. Using exponent rules, the exponent of an exponent just gives multiplication of the exponents. Here, the 4 is really the length of v, w, x, y, which is the length of M. So twisted conjugation of a general multivector M comes with an overall sign S, where the sign depends on both the length of the multivector M and the length of the versor R. I'm going to finish off this video with a warning. If you've been reading papers or watching videos on geometric algebra based on the work of a mathematician named David Hestenes, you might have heard people say that a spinor is defined as any sum of even grade elements in a Clifford algebra. This is not the definition of spinor that I'm using in this video series. I'm defining spinors as members of minimal left ideals in Clifford algebras. These two definitions are different, but they are related. I'll explain the relationship between these two definitions in future videos.